Well, in section 3 we'll talk about solving linear equations, and we'll mainly stick to systems which are square, which is the case if the number of equations corresponds to the number of variables. We'll introduce the idea of elimination, and we'll compute also matrix inverses using this same idea, and then we'll go to the LU decomposition of a matrix, and we'll see how it can be useful. So let's have a look at the system of equations AX equals B, and here A in this slide is general in the sense that it's in R M times N, so there are M equations and N variables. Okay, so we look at the product AX, and we've seen in the second video that there are two interpretations, and we'll start here with the row interpretation. Okay, so AX produces a vector, and from this row interpretation we know that the elements in the vector are constructed from the scalar product of the corresponding row with X. This leads to a number of equations, okay, M equations, and if you look at it, these equations for I going from 1 to M correspond to the equations of hyperplanes. Okay, so the question, is there a solution to AX equals B, is the same as, do the hyperplanes, the M hyperplanes, intersect? And you can of course have three solutions, three cases. Either there is no intersection, there is a unique solution, and the hyperplanes intersect in one point, or you have an infinite number of solutions. So this interpretation is geometrical in nature. Well, there is also a second interpretation of the product AX, and it's a column interpretation. Remember that AX, which produces a vector, in the column interpretation it's seen as a linear combination of the columns of A using the elements that are in X. Okay, so there is another interpretation to the linear system of equations which is algebraic in nature, and which restates the question, is there a solution to AX equals B, in another question which is there a linear combination of the columns of A that will produce B? Okay, so the solution X comes in the form of the parameters that will have to be used in the linear combination to produce B. Well, it's always good to have a look in a situation where things are simpler, so we'll work in R2 over here. So here is our system of equation AX equals B. Okay, so it's A here is a 2 by 2 matrix, and we'll start with the row interpretation. Okay, so we take this thing over here, and we know that it's producing a vector. Okay, where you take the first row of A times X, so this will produce X1 minus 2X2, okay, and the second element here will be the second row times the vector X, so this is 3X1 plus 2X2 is equal to this thing here. Okay, and as we have said, these are the equations of two hyperplanes, and in R2 a hyperplane is simply a line. So this is the equation of a line, and this is the equation of a line. So asking the question, is there a solution to this system of equation, is simply the same as asking, is there an intersection between those two lines? And the row interpretation is indeed geometrical in nature, and here we see that there is indeed an intersection between those two lines, and the intersection yields the solution, which is equal to x1 equals 3 and x2 equals 1. Okay, here we look at the column interpretation. Remember that this interpretation is algebraic in nature. So again, we have A, x is equal to b, and in the column interpretation you rewrite this as follows. So you say, well, ax is actually x1 times the first column plus x2 times the second column. Okay, and you say, well, it's equal to b 111. So is there a linear combination of the vector 1 3 and the vector -2 2, first and second column of the matrix A, that will produce B? And if you look at it, if you take 3 times the first column plus 1 time the second column, this indeed produces the vector B. Okay, so this is another interpretation of the system of equation, and of course it leads to the same solution. So now we introduce the idea of elimination, and it's a systematic way to solve linear equations. The idea is to produce what is called an upper triangular system, and this system can then be solved by using back substitution. We'll illustrate that in the next slides. So we'll introduce the idea of elimination, Gaussian elimination, and the production of a triangular system on this system of equation that we have used before. So we'll start here at the top left, and the element here is called the pivot. Okay, and we assume that this pivot is different from 0. We'll see what happens if it is 0. We use this pivot to produce a 0 below the pivot, and this is done as follows. So we take the second equation, okay, and we withdraw 3 times the first equation. Okay, this will produce a 0 over here, and we obtain an equivalent system. Okay, the advantage is that this system is upper triangular, okay, and that the variable x2 is now very easy to obtain. Okay, so x2 is this element divided by this element, and in our case it's 1, so we know now that x2 equals 1, and now we do what is called back substitution. So we take the equation that is above, we inject x2 equals 1 in the equation above, and then we take it to the other side, okay, and we solve for x1, and we see that x1 is equal to 3. Okay, so this is the solution. We can also look at the geometrical interpretation. The first line is remain unchanged, and the second line has been replaced by this horizontal line. Okay, so this is a very systematic way to solve a system of equations. Okay, some definitions here. We have already defined the pivot, and the pivot is a non-zero element that is used to do the elimination, and you see that this pivot is used to produce the zeros below the pivot. Then you have the multiplier. In this case the multiplier is 3, okay, and it's the entry that needs to be eliminated, this one here, divided by the pivot, okay, and this produces 3. So here you see the idea of the Gaussian elimination in all the details. You start at the left in the first equation, and you take the pivot. It should be non-zero. This is the case. You use the pivot to produce a 0 below the pivot. You use a multiplier, which is the entry to eliminate 3 divided by the pivot, so the multiplier is 3. And now you know that you can take this equation and subtract this equation times the pivot, and it will produce me a 0 over here. Okay, so you have this triangular form over here. You have a new pivot, which is 8. You divide the equation by 8 and you find the solution of x2. You inject it in the equation over here. Okay, x2 equals 1, so you have -2, and you take it on the other side. Okay, so this is Gaussian elimination explained on a very simple example. Okay, well, Gaussian elimination can break down in a certain number of cases, and here you have an example where it will break down and there will be no solutions. Okay, so we start from a very simple example, 2 equations, 2 variables, and we use our Gaussian elimination. We start at the top left with the pivot. We use it to compute the multiplier, so it's the entry to be eliminated divided by the pivot, and this gives us a 3 over here. So this equation minus 3 times the first equation produces this equation over here. So it's very obvious from this new equation 0 times x2 is equal to 8 that there will be no solution over here. Okay, so there are 2 interpretations. Again, this geometrical type interpretation and an algebraic type interpretation. Let's start from the system that is shown over here, and let's use the geometrical interpretation. It says that you have 2 hyperplanes that should intersect, okay, in order to have solutions. And here in R2 the hyperplanes are simply 2 lines. The 2 lines corresponding to these 2 equations are shown over here, and you see that they are parallel lines, and of course they cannot intersect, and this is why there is no solution. Okay, so in the algebraic interpretation you should look at the 2 columns of A, and this is A is the matrix 1 minus 2, 3 minus 6, and you should have a look, is there a linear combination of the columns, column 1 and column 2, that will produce B. But since the 2 columns are parallel, it's impossible to find a linear combination of these 2 columns that will produce B. You can only produce vectors that are on this line by linear combinations of C1 and C2. So again, we see, using another interpretation, that this system has no solution. This is kind of obvious to see from the Gaussian elimination. So every time that you end up with an equation like this one, 0 times a variable is equal to something that is not equal to 0, of course you will have no solutions. So here the Gaussian elimination breaks down, but for another reason, and in this case there will be an infinite number of solutions. So we start from yet another system of equations and we do our Gaussian elimination. We start at the top left, we have our pivot, the multiplier is simply the entry to eliminate divided by the pivot 3. We take the second equations minus 3 times the first equation, and this produces an equation that is this one. And in this case the equation 0 times x2 is equal to 0. Well, it has an infinite number of solutions. You can take whatever value, whatever real value for x2. So x2 is called a free variable. Okay, so in this case, if you end up with this type of equation, you have an infinite number of equations. So let's have a look at our 2 interpretations. The geometrical one, This consists in looking at these two equations, and well, there are hyperplanes, in this case lines in R2, and the question is, do they intersect? Well, they do intersect because they are the equations of the same line. Okay, so of course there is a solution, and there is even an infinite number of solutions. Okay, so in the algebraic interpretation, remember that A is 1 minus 2, 3 minus 6. Okay, and the question is there a linear combination of the columns of A, column C1 and column C2, that produces B? But in this case here, the vector B 1, 3 is on the line that is being produced by taking all linear combinations of C1 and C2. And here there are actually lots of combinations of C1 and C2 that will produce B. For instance, you can take 1 times C1 and 0 times C2. Okay, you can take minus a half times C2 and 0 times C1. Okay, so you see that there are lots of solutions, but what is important is that whenever you encounter an equation like that one, there is a free variable, and this will lead to infinitely many solutions. There are also cases when you do the Gaussian elimination when there is a temporary failure. Remember that the idea is that you start at the top left and you use a pivot, but if you do that here, you have 0 times x1. Okay, so I cannot take 0 as a pivot because by definition a pivot is different from 0. So what you can do then is to shuffle the equation. Okay, so the second equation becomes the first one. Okay, and then you can continue the procedure. Start at the top left and I find a non-zero pivot. Of course, in this very simple 2x2 example, you're finished, right? Because the system is already then in triangular form. Okay, if you have more complicated systems with more equations and variables, of course this trick can still be used. Well, let's take an example that is a little bit more complicated with 3 equations and 3 unknowns, and apply our idea of Gaussian elimination. Okay, so we start at the top left and we have found our pivot, which is 2 over here. Okay, so now we are going to construct the multipliers. Okay, so here you need to produce a 0 at this entry, so you need to take the entry divided by the pivot, it's a 2, and here you take the entry divided by the pivot and it's minus 1. And then what you do is take the third equation minus the first equation times this multiplier minus 1. Okay, this produces this equation over here, so you have produced here a 0, and then you take the second equation, okay, and you subtract the first equation times the multiplier over here, and this produces a 0 over here. You might be tempted to say, well, I'm not going to do third equation minus first equation times minus 1. I'm going to make a plus here and a plus here. If you do this for systems of equations, that will work perfectly. Okay, but I advise you to leave it as it is, because this multiplier here will be imported for the A equals LU decomposition, and there it will be important that you have the multiplier when you do a subtraction over here. Okay, you could change things, with respect to what I've just explained you for the solution or the elimination in systems of equations, but when you compute the decomposition LU, it will be important to have this multiplier as defined over here with a minus sign over here. So I would do my exercises always with a minus sign over here, just to make sure that I don't make any mistakes when I do my LU decomposition. Okay, so we have now arrived at this situation here, and we want to arrive at a triangular form, and we have something that is annoying us here. So we take the second equation and we go further and we obtain a new pivot. It's non-zero. Okay, we want to produce a 0 over here, so the multiplier is the entry 1 divided by the pivot, and you have a 1 over here. Third equation minus the second equation times the multiplier 1 will produce a 0 over here, and we have now our system that is in triangular form, upper triangular form. So we can now start with our back substitution. So we divide the third equation by the pivot and we obtained x3 equals 2. Okay, so this leads to the following equivalent set of equations, right? So since we know that x3 equals 2, we can inject it in the previous equation. This is what is done over here, and we find the solution for the second variable. Okay, so we know that x2 is equal to 2. So we had injected x3 equals 2 also in the first equation, minus 4. Since we have now our solution for the second variable, we can also inject it in the first equation, right? And now we can solve for x1. Okay, so we take these terms here on the other side and we divide by 2, and if you do that, you find that x1 is equal to minus 1, and we have found the solution of our system of equations. In this case here, there is a unique solution. We'll do some more exercises and see that there of course are other cases where there are no solutions or an infinite number of solutions. Well, when doing Gaussian elimination, we have used so-called elementary operations. There are 3 types of elementary operations. The first one is to interchange 2 or more of the equations, and this can be interesting if you're blocked because you have a 0 pivot. Okay, the second elementary operation is to replace an equation by a non-zero multiple of itself, and the third elementary operation is to replace an equation by the equation itself, from which you subtract a multiple of another equation. Okay, and this is exactly what we're doing in Gaussian elimination to produce zeros. So if you start from a system with linear equations L and you use elementary operations to produce a system of equations M, they are equivalent systems. Okay, and since they are equivalent, well, they will have the same solutions. Well, when you do the Gaussian elimination on the system AX equals B, you have to write the variables x1, x2 and x3 several times, so it's kind of heavy on notations. What is usually done then is to forget about these variables, you don't write them, and you use a augmented matrix that is shown over here, and you take simply the matrix A and you write B right next to it. So you do the same row operations that you do on A to produce this upper triangular form on A, well, these row operations you do also on B, okay? Well, this is illustrated on the example that we have tackled before, and as you notice, well, we don't write the variables x1, x2 and x3, we simply write the matrix A and we put the vector B just right next to it. And the idea is that we do row operations that we have done before with these multipliers and these subtractions to obtain a form of the matrix that is upper triangular, okay? This is done by row operations, and if you do the same row operations on the vector B, you end up with this independent term over here, okay? So this last equation has to be seen as 4 times x3 is equal to 8, and the second equation is, for instance, x2 plus x3 is equal to 4, and the first equation is 2x1 plus 4x2 minus 2x3 is equal to 2, okay? And you can kind of use this or this directly to do the back substitution. If you're used to it, it's much quicker and you don't have to write these variables x1, x2 and x3 a million times. Well, let us take an example of a system of equations, and here it is. So I've written it in the augmented form, and now we can start the elimination procedure. So here is our pivot. Okay, so we're going to produce zeros below the pivot. And what we need is to compute the, let's choose this color here, the multiplier. To produce a 0 here, you take the entry divided by the pivot, it's minus 3, and here 5 divided by the pivot, it's 5. And now we are ready to produce the next augmented matrix. Of course, the first line remains the same. We're going to produce zeros over here, and if we do the calculations, we'll have a 7 over here, a minus 11 over here, and a minus 10 over here. So we're going to do the same thing for the third line. This gives a minus 7, 11, and here 7. Okay, so we had our pivot here, we have our next pivot that is over here, and now we want to produce a 0 below the second pivot. So we need to do this elementary operation, and the pivot, the multiplier will be minus 1. Okay, and we end up with the last augmented matrix. Now the two first lines will be kept. I have a 0 over here, a 0 over here, a 0 over here, and a minus 3 over here. Well, let's have a look at the interpretation of this augmented matrix, this last augmented matrix. We can write, of course, all the 3 equations, but here it's only necessary to write the last one. And we see that 0z is equal to minus 3. So obviously there is no solution to this equation. There is no z that multiplied by 0 will give me minus 3. So obviously this system of equations has no solutions. and this completes this exercise. So let's do another exercise here. I've already put the system of equations in the augmented form, and we can start the elimination procedure. So here's the first pivot. I want to create zeros below the pivot. Okay, now I need to compute my multiplier, so it's the entry that I want to make 0 divided by the pivot. I have a 2 over here and a 3 over here. So let's produce the second augmented matrix. Obviously, again, this first row will remain the same. I'll have a 0 over here and a 0 over here. I will produce a 1 over here, a -2 over here, and a 2 over here. A 2 over here, a -4 over here, and a 4 over here. So obviously I want to bring the system in upper triangular form. Here's my next pivot, and in order to bring it in upper triangular form, I need to create a 0 over here. And my multiplier will be the entry that I want to make 0 divided by the pivot, so it is a 2 over here. And let's continue. Now I can copy the two first lines. Obviously I have 0 here, I will have a 0 over here, but I will also have a 0 over here and a 0 over here. Okay, so this is my last augmented matrix, and again I can write the equations. I will only write the last one. I have 0, z is equal to 0, so z here can be anything. It's a free variable. I will simply write z is equal to a, where a is any real number. Okay, so I will write now so I'm starting from the bottom. Write the second equation, so it's y minus 2z is equal to 2. So obviously y is 2 plus 2z, but z is equal to a, so it's 2 plus 2a. And now I can write the first equation, x plus 2y minus 3z is equal to 1. So x is minus 2y plus 3z plus 1. And now I inject my z over here and my y over here. So I have minus 4 minus 4a plus 3a plus 1 is equal to, write it over here, I'm not sure it is recorded on the screen, minus 3 minus a. Okay, and this is my x. So my solution is well, let's write it like this: minus 3 minus a, 2 plus 2a, and a, with a in R, a real number. So clearly here we have an infinite number of solutions. So we have had two types of exercises. The one in the slide with a unique solution, the previous exercise with no solution, and here you have an infinite number of solutions. Well, you can do also elimination using elimination matrices. Okay, and suppose you want to do this operation, so you subtract from row I row j times a multiplier Lij. Well, you can construct the equivalent elimination matrix by taking an identity matrix in which you replace the entry ij by the multiplier with a minus sign. Okay, so for example, if you want to implement this operation here, so we want to create a 0 by subtracting from row 2 times row 1. Well, you take your identity matrix, and since you want to create a 0 in element 2, 1, you replace the 0 by the multiplier, okay, with a minus sign. So we have seen in the previous slide that we can construct this elimination matrix, and it's a bit magical, right? Remember that this elimination matrix was implementing the following thing. So you replace row 2 by row 2 minus 2 times row 1. Okay, so is there an explanation for that? Well, if you remember this row interpretation of the product E2A times A, you can kind of understand where it comes from. And in the row interpretation, what you do is you take the first matrix and you consider it as rows that are one on top of another, and the product will be such that the first row, okay, well, it's the first row of the first matrix here, the elimination matrix, times A. In the second row, it will be the corresponding row of the first matrix here, the elimination matrix, times A, and so on. Well, in our case, the first row of the elimination matrix is 1, 0, 0, the second row is minus 2, 1, 0, and the last row of the elimination matrix is 0, 0, 1. Okay, and we had seen that this can be seen as a linear combination of the rows of A using this coefficient. So this is saying this is 1 time the first row plus 0 times the second row plus 0 times the third row. So using this elimination matrix E21, you leave the first row untouched. The second row will be changed. Oh, that's normal, huh? Because you want to implement this thing here. Well, it will be minus 2 times the first row of A plus 1 times the second row of A. And of course the third row will be unchanged. So indeed what we have implemented over here using this elimination matrix corresponds to what we wanted to implement. Well, let's construct the elimination matrices for our example that we had previously. So the first thing that we do is create a 0 over here, and the underlying matrix, elimination matrix, we'll call E21. Remember that you have to take a identity matrix. Okay, all the rest are zeros, and what you do is at the place E21 where you create a 0, you have to take the multiplier and you put a minus sign in front. Okay, so this is elimination matrix E21. E31 will be, well, you do the same thing. It's an identity matrix where the element that you want to make 0 is replaced by the multiplier with a minus sign. So this will give me a 1 over here. And the last elimination matrix, well, you want to create a 0 in element 3, 2, so it will be called E3, 2. You take your elimination matrix and you start from the identity matrix, and you take your multiplier and you put a minus sign in front. So these are the 3 elimination matrices in this example. So here are the 3 matrices that we had constructed previously, and you see that if you pre-multiply your augmented matrix, okay, here it is, by these elimination matrices, you obtain the final augmented matrix. It's important to respect the order of operations, right? You have first produced a 0 over here, and then a 0 over here, and then a 0 over here. So you should have first pre-multiply by E21, then E31. These two you could swap, okay? But this one you have to keep as last, because it assumes that the previous calculations have been performed. So order is important over here. So remember that in Gaussian elimination sometimes you have to exchange rows because you have ended up with a 0 pivot, right? And you want to continue the procedure. Well, permutation of rows, interchanging rows, can be done with a matrix that we call a permutation matrix. Okay, so if we want to construct the permutation matrix that interchanges row 1 and 3, we have to start from the identity matrix, and I'll take a 3 by 3 example here. 1, 1 on the diagonal and zeros everywhere, so this is my identity matrix. And if I want to interchange rows 1 and 3, I start from the identity matrix and I perform this operation and I end up with the following matrix: 0, 0, 1, 0, 1, 0, and 1, 0, 0. So when I pre-multiply a matrix A by this permutation matrix, what I will do is interchange rows 1 and 3. This is what I need for elimination. Okay, you can do something similar with the columns of A, but then it's post multiplication. So you have to do the following operation: A times P1, 3, and see that you can also obtain this matrix here by exchanging the columns. Okay, and if you do this operation over here, what will happen is that you will obtain the matrix A with columns 1 and 3 that are swapped. So remember that Pij times A will interchange the rows I and j of the matrix A. Okay, so suppose now that you pre-multiply this by Pij again, this matrix will be the matrix A with the rows I and j interchanged. By pre-multiplying, okay, you'll interchange the rows again and you'll end up with the initial situation. So this is equal to A. This means that this matrix here is the identity matrix. This is the property that is written over here. Okay, so Pij squared is the identity matrix, but this is also means that the matrix is equal to its inverse. We'll talk about inverses later on in the course. So you have Pij equal to its inverse, but you can also see by taking a few examples that Pij is equal to its transpose. Let's take the example P1, 3. It interchanges row 1 and 3. So you have 0, 0, 1, 0, 1, 0, and 1, 0, 0. Okay, this is equal to P13 transpose. So permutation matrices, elementary permutation matrices, and that interchange one row, well, they are a bit peculiar because Pij is equal to its transpose and to its inverse. So again, this sounds a little bit magical. So why is this matrix here, P13, going to interchange the rows of A? Well, again, you can look at the row interpretation of this product of matrices, and in the row interpretation, well, you have to see P13 and subdivide in rows, right? And the product will be such that it's a matrix where the first row is a linear combination of the rows of A obtained from the first row of the permutation matrix. So the first row of the product, it's simply, well, the first row or the corresponding row times A, and you have the same result for all other rows. Okay, so each row is constructed from the corresponding row of the permutation matrix times A. Here these rows are simply 0, 0, 1, 0, 1, 0, and 1, 0, 0. Okay, so the first row over here, as I said before, it can be seen as a linear combination of the rows of A, and it's 0 times the first row plus 0 times the second row plus 1 time the last row. So this is why you end up here with the third row. Here you'll select with the 1 over here the second row. Okay, this row has remained as is, and here you will select the first row. So we have indeed interchanged row 1 and 3. So we have seen that we can also use this permutation matrix for post multiplication. So you do A times the permutation matrix, and this will interchange column 1 and 3. So you can see this from the column interpretation of the product A times the permutation matrix here. So in this interpretation, you subdivide the permutation matrix in columns, okay, and the resulting product can be written in terms of columns, and each column is A times the corresponding column of the permutation matrix over here. Okay, so column 1, column 2, column 3. So here column 1 is this vector, column 2 is this vector over here, and column 3 is this vector over here. So this is A times X. This is X here, and we had seen that this produces a linear combination of the columns of A using the elements that are in the vector. So it's 0 times the first column plus 0 times the second column plus the third column. Okay, so you see that indeed the third column is now the first column of this product. So we see that we have indeed interchanged columns 1 and 3, because here you see that indeed with the 1 over here you select the first column, and with the 1 over here you select the second column. Well, I've given you a lot of exercises that are online, and it's always a good idea to check things with Matlab, with the advantage that you learn to work with Matlab and that you work with matrices, for instance these elimination matrices. So let's have a look at our example of the slides, and I've already put here the augmented matrix. Let's have a look at it, and here it is. Okay, so 2 is our pivot over here, and we want to create zeros below the pivot. Okay, so the multiplier to create a 0 in 2, 1 will be 4 divided by 2, 2. Okay, so we can work in our M file here and produce the elimination matrix E21. You start from the identity matrix, okay, and in element E21 you have to put minus the multiplier, and the multiplier was 2 over here. Let's have a look at E21 times A augmented. Okay, it indeed produces a 0 in element 2,1. So we can do the same for element 3,1. So we take the element divided by the pivot, the multiplier is -1. So let's copy this. So this is now elimination matrix 3,1, 3,1, and element 3,1 we take minus the multiplier, so minus 1, it's 1. Okay, let's now pre-multiply by E31 and let's have a look. Indeed, this is what we obtain. We have produced a 0 in E31. So the next pivot is 1. We want to produce a 0 in element 3,2. So 1 divided by 1, the multiplier is 1. So elimination matrix 3,2. We take minus the multiplier, so we have -1 here, and we have E32. We pre-multiply and let's have a look. And indeed we have produced a 0 in element 3,2. Okay, I've said that order is important, so let's have a look at that. So let's reverse the order. So E21, E31, and here E32. And indeed this was correct, and this is with the order reversed, and so we obtain something quite different. Okay, just want to show you, for instance, elimination 2,1, elimination matrix 2,1, elimination matrix 3,1, and elimination matrix 3,2. Okay, so you have started from the identity matrix and you have just changed the corresponding element where you want to create a 0. Well, I've added another example here that comes from the exercises that I've put online, and this is a bit more challenging because I've added letters in the system of equation. You have A and B here, that can be any real number. I have already put the system in augmented form, so we can start with the elimination. Okay, so we start with the pivot over here at the top left. We have already a 0 over here, so that's for free. We have to produce a 0 over here. Okay, so we have to do this type of operation with the multiplier, which is the entry that we want to make 0 divided by the pivot. So we have a 2 over here, right? So in this case we can just copy the first 2 lines, 0, A, 5, 10, 2. Oh no, that's not a 2. I cannot copy this one. It's a 0, of course, over here. Okay, and this will produce me a 3. This will produce A minus 2, and this will produce B minus 6. Okay, so I have produced zeros below the first pivot, and we continue. Oh, we have a A over here. Okay, remember that pivots must be different from 0, and nothing says that A could be different from 0. So if we take this one as a pivot, let's do this for the sake of the argument. We want to produce a 0 over here. We would have to do something like this with a multiplier, that is the entry divided by the pivot. Okay, we don't like this because we could be dividing by 0. Okay, so let's go back a little bit and do something else. What could we do? Well, we could interchange the rows. We could do this. Okay, so we'll just copy the first line. We write now the third row becomes the second row. We have the second row here, 5 and 10. Okay, so this was our first pivot. Now we have a pivot of 3, right? So we can simply do the usual operations. We take the entry that we want to make 0, a divided by the pivot, so our multiplier is a over 3. Okay, so let's continue over here. So of course the two first lines will remain the same. And we'll have, of course, a 0 over here, a 0 over here. Here we'll have 5 minus 8 over 3 times a minus 2. Okay. And over here we'll have 10 minus a 3 times b minus 6, right? We can maybe multiply the third row by 3 and we end up with, I'll write it, take a bit more space, 0, 3, a minus 2, b minus 6, so I have 0, 0 here. I'll have 15 minus a minus 2, and I'll have 30 minus a b minus 6. Okay, so this is our final augmented matrix, and now we should start discussing what will happen using a and b. Well, I've removed now the intermediate results, and we should start discussing the results based on the values of a and b. Well, we'll mainly have a look at this value here. Okay, and we'll call it 1, and this value over here, and we'll call it 2. Okay, so we can look at the special values that make 1 here 0, and if you look at that, you'll see that a equals 5 and a equals to minus 3 are special values because they make the value 1, okay, is equal to 0. So let's look at a first case where a is different from 5 and a is different from 3. Okay, in this case you have a matrix A that is upper triangular, and you can do back substitution, and whatever the value of b, there will always be a solution. This means that there is in this case a unique solution. Okay, so if a is different from 5 and a is different from -3, sorry, you have a unique solution. So now we can continue our discussion based on a, and we'll take a is equal to 5. Okay, so we can rewrite 2, and 2 becomes 30 minus 5 times b minus 6. Okay, so this is 2, and we see that there is indeed a special value for b here. If b is equal to 12, okay, then 1 is equal to 0 and 2 is equal to 0. Okay, and you have an equation of the type 0z is equal to 0. Okay, so a is equal to 5 and b is equal to 12 will lead to an infinite number of solutions. Well, if you take a equal to 5 and b equal to, well, different, from 12, then 1 is 0, but 2 here will be different from 0. Okay, so you end up with an equation of the type 0z is equal to something that is different from 0. So you have no solutions. Okay, so we have to do something similar with a is equal to -3, and then 2 becomes 30 plus 3 times b minus 6, and there is a special value that makes this one 0, and it's b is equal to -4. If you put b equal to -4 here, you have the situation where 1 is equal to 0 and 2 is equal to 0. Again, you have this type of equation, 0z is equal to 0. So a equals to -3 and b equals to -4 is a special case where, again, you have an infinite number of solutions. Whereas if a is equal to -3 and b is different from -4, well, you end up with a case where 1 is equal to 0, but 2 is different from 0. So you have an equation of the type 0z is equal to something that is different from 0. So this leads to a system without solutions. So there are no solutions in this case. Okay, so now we have covered all situations, and we have ended up with values of a and b where you have a unique solution, an infinite number of solutions, or no solutions.